All right, so let's do one more part here regarding section 3.6. And the last item here from 3.6 deals with something known as related rates, which is a special type of implicit derivative. Related rates occur when you have a function that's in terms of another variable. You have a function of two variables that's actually in terms of a third variable. All right, so let me get this set up here. And let's talk about these related functions. Okay, everything's set up. Look at this. All right, so sometimes a function, or sometimes two variables in a function, I'll specify instead. And a function in an equation could be functions of a third variable. And for this section, and for our class, we're going to be focusing on usually time. So usually time represented by t. Okay, so like say, for example, a related rate could be like, say, the area of a rectangle, right? The area of a rectangle, known as A, is a function of length and width, L and W, which is our two variables that we utilize for this equation, or two inputs for this equation. Oops. So a rectangle A is a function of two variables, length and width. So here we have these two functions that we input, a value for L, a value for W, to find the value of a third variable A, where A represents the area of that rectangle. Or like say another example, like say business-wise, price P and quantity X could be related to time T, or that quantitative quantity. Or the price of an item, the price that we have set on an item, and how much of that item we're going to either produce or sell, that can be related to how much time has passed. Right? Usually new items, they sell at a high price, low quantity in the beginning, but then as time goes on, the price starts to come down, and the quantity of the item, how much is being sold, tends to go up. Okay? So let's look at the steps when it comes to solving these related rate problems, which won't be too different from what we have seen so far throughout this section here. Okay? So again, a related rate is the change of rate, or the change of rate, the rate of change, I should say that, rate of change. The rate of change of a variable relative to another variable. Okay? In this case, we want to look at the change of the rate of change of one variable related to two other variables. Now, the first step when it comes to setting up these related rate problems, the first step is, again, we're going to assume that our third variable of interest will be time. So the first step is let's determine the variables that are changing with respect to time. We call WRT, means with respect to. So first we got to figure out what are the two variables of interest that are changing along with time. Second step, let's define an equation that is relating these two variables. Or I should say, well, relating these variables. I'll just leave that as that, as general, relating these variables. Usually it's an equation that's relating our two variables of interest. Okay? And then what we do is, once we have defined that equation relating our two variables of interest that are changing with respect to time, the third step is when we start doing implicit derivatives again. Because in the third step, we're going to differentiate both sides of this equation but in this case, with respect to that third variable, time. In other words, we're going to multiply both sides of this equation by d over dt. Okay, that third variable that we're trying to find the related rate with respect to, d over dt. Okay, and then the fourth step is to substitute once we have gotten d over dt, or once we have gotten d blank over dt by itself, substitute any given values into our equation. So I substitute in our equation any given values, and also any related rates. Any related rates with respect to time t. Okay, and then solve for the remaining variable, or the remaining rate slash derivative that we are trying to find. Okay, so for these type of problems, we're also going to be given some values. We might be given a value or two of our two variables of interest, and then for one of those variables of interest, we're also going to be given a related rate already. All right, we're going to be given a related rate derivative of that variable respect to time. So we plug in what we know, and then solve for the remaining derivative, solve for the remaining differentiable that we're trying to identify. Let's do a problem involving these steps here, so we get an idea how to solve these related rate problems. Let's see if I have enough room here. I might. Let's see. Oh, cricket line. Oh, now when we make a line. Okay, that should be good. Okay, let's set up an example here. Suppose that for this example, suppose a company's revenue from selling X units is defined as, say, R equals 1,000X minus X squared. Okay. If the sales amount are increasing at a rate of 80 units per day, find how many or how rapidly the revenue is changing, or I'll say growing, per day when 400 units have been sold. Okay, yourself, which is usually not acting up. All right, here we want to figure out if this is the amount of revenue that this company makes based on the amount of based on the amount of units that they sell. Then if we're told that the sales amounts are increasing at a rate of 80 units per day, let's figure out how rapidly the revenue is going to change. It's going to be changing per day if we sell exactly 400 units. Okay, so first step, determine the variables that we're interested in that are changing with respect to time. In this case, time is being represented by day. Okay, so let's look at what we're trying to look at. Let's look at what we're trying to see changes per day. We're trying to see how the sales amount are changing per day, and we want to find out how the revenue is going to be changing per day. So here we have our two variables of interest, the sales amount and the revenue. Okay, so sales per day, which is known as X, the number of units that we sell is being represented by X here. So sales per day, X per day, or in other words, X per T. And then we want to see how the revenue is going to be changing per day. So revenue per day. So revenue is our other variable of interest. I'll say capital R per day. In other words, RPT. Okay, where T is representing day. Okay, so that's the first step. Identify your two variables that are changing with respect to our variable of time. Second step, find an equation that's relating our two variables of interest, which is given to us directly in this problem. What is the equation that's given to us that's relating the amount that we sell per day and the revenue that we make? Right there in the revenue function. So here we have that revenue equation already that's relating X and R. Okay, so here our equation relating our two variables are r equals 1000x minus x squared. Okay, so once we identify that equation relating our two variables, then the next step is to take that equation and then differentiate both sides of it with respect to that third variable of time. Okay, so now it's implicit derivative time. Okay, so let's take this step by step. So here we have this equation again. Here we have r equals 1000x minus x squared. And what we're going to do, similar to what we did for implicit derivatives, is we're going to take the derivative of both sides of this equation, but in this case, with respect to time, d over dt. So we're going to multiply both sides of this equation by this differential of d over dt. Okay, so similar to what we have done before, take the differential and distribute it to each term of both sides of this equation. So on the left-hand side, we're going to be taking the derivative with respect to time of r equal to derivative with respect to time, of 1000x minus derivative with respect to time of x squared. Okay. So, like we have done before in this section, now we take the derivative of each term that we have with respect to this variable in the denominator. But as we take the derivative of each term, do not forget that for the numerator of our differential, we have to specify the variable that we're taking the derivative of. All right, so here we have our r variable. So in this case, we're taking the derivative of r with respect to t. So that would be our differential on the left-hand side. dr over dt. And what's the derivative of a variable to the first power? Just 1 in this case. The derivative of r is just 1. Equal to, for this next term, we're taking the derivative of x term. So our differential is going to be dx over dt. Taking the derivative of an x variable with respect to time. And what's the derivative of 1000x? 1000. Minus another derivative of x with respect to t. And the derivative of x squared with respect to time is going to be 2x. Okay. Let me simplify this a bit more. So here we have d over dt times 1, which is just d over dt. So dr over dt equal to, now notice what do these two have in common? These two have a common factor of dx over dt. While we're at it, let's take out that common differential of these two terms. So we're going to have 1000 minus 2x times dx over dt. Okay, but let's see if we're finished here. Again, we want to rewrite this. We want to take this equation and solve for the differential for the related rates that we're trying to solve for. Let's see, what are we trying to find here? Use a different color. We're trying to find, let's see what's given to us. So company's revenue from some X amount of units is this equation. And then it tells us in the second statement here, if the sales amount are increasing at a rate of 80 units per day. If the sales are increasing at this rate of 80 units per day. What do you think that 80 is representing? If it's the value of the change in the sales with respect to day. Okay. Again, X per day, sales per day, X per T. If this is how much the sales are changing per day, then this 80 is representing our differential of dx over dt. So that's our dx over dt 80. The change in x over the change in time. And the amount of sale, in this case, positive 80 because we have an increase in value. So this telling us the sales are increasing at a rate of 80 units per day, per time. So that's our dx over dt. Okay, and what are we trying to find here? We're trying to find how much the revenue is growing per day. How much the revenue is growing per day. Meaning we want to figure out the derivative, the change in R, so dr, with respect to time. That is the rate that we're trying to solve for. We want to figure out the change in the revenue with respect to time. Okay? So this is what we're trying to solve for here, dr over dt, which we already have by itself here. Oops, in our equation, dr over dt. Is it acting up? No. All right. So here we have dx over dt. It's going to tell us 80. We're trying to find dr over dt, but we also need a value for x, just the amount of just the amount of units that are going to be sold here. And so we also need a value of x. Well, let's finish that second statement. Find how much the revenue is growing per day when 400 units have been sold. When we have sold 400 units, meaning let's find how much the revenue is changing when x is 400. So there we give directly the value of that variable of x. All right, so if we know that sales are increasing at 80 units per day, then how much is the revenue going to change if we have sold 400 units on that day? Okay, so all we have to do next is just take our equation and plug in what we know and solve for the unknown. All right, so this will be 4 and 5 together. So these steps 4 and 5 pretty much go together here. Okay, so actually let me do it like this. So step 4. So we know that x is going to be 400, and we know that dx over dt is 80. So now for step 5, so now that we identify our given values, for step 5, plug in what we know into our equation that we have here. So we're going to take dr over dt, which is our unknown rate, our unknown differential that we're trying to solve for, and it's going to equal 1,000 minus 2 times x, where x is 400, times dx over dt, where the rate of change in sales over time is 80. So times AB. Okay. To give us, subtracting these two, multiplying this out, gives us a value here of 16,000. And since we're talking about revenue, this is $16,000. Okay, so what is this telling me? This is telling me here that if sales are increasing at 80 units per day, then our revenue will be growing at $16,000 per day if or when 400 units have been sold. So if we have we're assuming some constancy here, some constants here. We're assuming that if the amount of sales are increasing at 80 units per day, then if we sell 400 units, our revenue is going to grow by $16,000 per day. All right. So here we have an implicit derivative of a third variable. Notice our initial equation, our direct equation here, does not even involve t. But we can find the change of an equation, the change of a variable, with respect to an unknown, an implicit third variable. All right. And just to be safe here, I'm gonna pause this part of the video and make one more part and do 2 more examples of these related rate problems. right? Just to be safe, just to make sure that this uploads correctly.